Alright guys, let's take a look at section 4.4, and this is a very short video, but I'm just going to do one quick example on curve sketching. And we have Desmos to help us graph these functions most of the time, but we do need to have some basic skills on how to graph some of this stuff by hand, and how we would use the calculus that we've learned in the last couple of lessons to help us get an accurate sketch, or at least get a general idea of what the shape of the graph would look like. I've got some steps here that are sort of a rule of thumb you can follow whenever you're asked to sketch a graph. And every graph, you're not going to use all of these steps, but use the ones that you need enough so that you get an accurate sketch. So step identify the domain of the graph and any symmetries the curve may have. This step, is sort of just to get you introduced to what's happening with the function. And really, I would say just focus on if it's a polynomial, maybe if it's an even or odd function. Remember to look at the powers. You can tell whether it's even or odd and decide if it's got any symmetry that way. And it may not have symmetry, and that's okay. Step 2, identify any x-intercepts and any y-intercepts. And if it's a function, there should just be one y-intercept. Find the first derivative and any critical numbers. Determine where the curve is increasing and decreasing. So there's where the calculus comes in, using that first derivative and the number line analysis. Determine any local extrema. So those would be your local max and your local min. Find the second derivative and any possible inflection points. And finally, determine concavity. And again, you don't have to do all of these steps, but enough to get the graph. And if you need to plot additional points, you can always do that. So let's do one quick example here. So I'm going to sketch the graph of this polynomial. I'm going to do my best here to use those steps above to get a nice image. And put your graph over here so you have a little bit of space to work. The domain I'm not going to worry about. This is a polynomial, so we know the domain would be all real numbers. The symmetry, however, we would look at the powers, and remember the rule from pre-calculus. If the powers are all even, then it's an even function and would have y-axis symmetry. If the powers are all odd, it would be an odd function and have origin symmetry. If they're mixed, as they are in this example, then it would not have any symmetry. So that doesn't do a whole lot for us, but it just gives us something to remember as we're sketching it. No symmetry for this graph. Step 2 is to find the intercepts. So let's start with the y-intercept. That's a little bit easier. Remember, to get the y-intercept, you let x equal 0. So I've got y equals, I'm using y instead of f of x, same thing, 0 to the 4th minus 4 times 0 cubed plus 10. So my y-intercept is going to be at 0, 10. For the x-intercept, let's go ahead and let y equals 0, so I'm going to set 0 equal to the function. Now, it gets a little tricky here. If you can factor it, go ahead and factor it and use the zero product property to solve it. In this example, it does not factor. So what that means is it's a 4th degree polynomial. That means the intercepts are going to be some decimals, and I'm going to skip the details then for this, and I'm not going to worry about the intercepts. And that's why I say take these steps with a grain of salt. If it's a complicated function and the intercepts would require maybe technology to solve and find those values or some higher level algebraic techniques, then don't worry about it. We'll get those later. We don't have to have the exact intercepts. But if it is something we can find by factoring, go ahead and do that, and that'll help us kind of get a sense of where to put our graph. If not, we'll figure it out. Perhaps the extreme will help us get a sense left to right of where our graph needs to end up. So let's go ahead and look at the first derivative. So the first derivative would be 4x to the 3rd minus 12x squared. And then we want to know where the function's increasing and decreasing. So that I'm going to set equal to 0. Fortunately, that does factor. I'm going to take out a 4x, and that leaves me, no, a 4x squared rather, and that leaves me with x minus 3, I believe. Yep, so 4x to the 3rd, that's it, just double checking. So my critical numbers are at 0, 3. So my critical numbers are 0 and 3. So I'm going to figure out where this is increasing and decreasing doing my number line analysis. I'm going to label this F prime, so 0 and 3 go here. If I choose a test point to the left, I'm going to get a negative value. If I choose a test point in between, I'm going to get a, let's see, if I try like 1, for example, I'm going to get a negative value. Yep, okay, and then on the right, if I choose, say, 4, I'm going to get a positive value. All right, so let's take a look at what this means. So this means that F is going to be decreasing, and then it's still going to be decreasing, and then at 3, it's going to switch to increasing. So what does that tell us about local extrema? Well, at 0, nothing's happening, but at 3, we will have a local minimum. So we're going to have a local minimum at x equals 3. And because we're sketching this, I'm going to go ahead and get the corresponding y value if I plug 3 into the original function. And I'm going to use my calculator here. And I'm getting a corresponding y value of negative 17. All right, let's now look at the second derivative and concavity. So for the second derivative, we've got f double prime equals 12x to the second minus 24x. So I'm going to set that equal to 0 to find possible inflection point locations. I'm going to factor out a 12x, and I'm left with x minus 2. So my possible locations are 0 and 2. So I'm going to come over here. I'm going to go ahead and do a number line analysis for the second derivative to talk about concavity. To the left of 0, let's say we try a negative 1. I get a negative times a negative, which is a positive. So that means we're going to be concave up. And then in between, let's say at 1, I'm going to get a positive times a negative, so a negative. That means we're going to switch to concave down. And then at 3, for example, we're going to get a positive, so I'm going to be back to concave up. Now, let's actually get those points of inflection because, again, we're going to graph these. So inflection points, we know there's going to be one at 0. So 0, 10, remember, was the point earlier we had. And then at 2, if we substitute 2, we get a corresponding y value of negative 6. So what I'm going to do, because I do know certain points on the graph, I know 0, 10 was the y-intercept. So I'm just going to kind of put that up here. And then I know 2, 6 was a point on the graph, so I'm going to put that here. And I know negative 17 was a point on the graph here. So let's talk about each of these little sections. So from up until we get to 0, we want to be concave up, but decreasing. So I'm going to come up, and I'm going to start way up high, and I'm just going to make the graph sort of smiling at you. Let me get rid of this stray mark I have right here. Oops. So we're decreasing, oh, this is messy, decreasing, concave up. And then, let me clean that up a little bit. Let me make that a little neater. It's tough to do without graph paper. So when we do these in class, I'll see if we can get some graph paper going. All right, so let's try that again. So we're going to be decreasing, concave up. Here, let me clean this up. I keep trying to clean this up a little bit. Let me do this one more time. All right, so we're going to be from 0 to 2, we're going to be decreasing still, but concave down. Then when we get to 2, we're going to switch to concave up, still decreasing, so it's going to kind of have an inflection point here. And then it's going to switch to increasing, but still be concave up. There we go. So we've got a graph that looks like this. Let's go ahead and extend. This is y, this is x. Yeah, so decreasing, concave up, decreasing, concave down, decreasing, concave up again, and then increasing, concave up. And that's our graph. So you can see there's no symmetry like we expected. It's got one local minimum down here at 3, negative 17, and it's got 2 inflection points. So at 0, 10, and 2, negative 6. And we'll do a little bit of practice with this in class. We're just looking for a basic sketch, and that's all we need to do.